First one, I gave you vector A, and the components were 5, 9. I graphed it over here, right? The components being 5 over and 9 up. So I sketched the vector. The magnitude of the vector is the size of the vector, and we know we're just going to use the Pythagorean theorem for that, and to get 10.3. To find the angle here, again, we're almost always going to find the angle with respect to the horizontal. So I'm going to use, say, the tangent of the angle is 9 over 5, which really says the angle is inverse tangent of 9/5, and I get 60.9, and visually that does make sense, right? It's going to be an angle greater than 45 because I'm way higher than I am over, and it is in the first quadrant. We might call that north of east. All right, here's an application question of why we would add vectors together. The vectors are given in component forms. We have a plane flying at 200 meters per second east, 40 meters per second north. We encounter a wind that's 10 meters per second west and 30 meters per second north. Here's the picture of it. So the plane's flying right and a little up. The wind is going left and a little up. If you look at the resultant, graphically we add those things tip to tail, and it doesn't matter the order, but I started with the plane and I added the wind to the tip of this. And the resultant then is that dotted line. The resultant is the net combination of those two vectors. And so when we add vectors, we add their components. So I just took the 200 plus the negative 10 to give you 190, and the 40 and the 30 to give you 70. So the plane plus the wind is going to be now flying 190 meters per second east and 70 meters per second north. And if I looked at the size of that thing, meaning the magnitude of the vector, and in this case, that's the speed, the magnitude of the velocity vector, I get this 202, where the original one, if I do the Pythagorean theorem on the original plane all by itself, is 204. And so in this case, the actual wind slowed us down and bent us more north. Remember, the original plane looks like this, and the result of the wind is the dotted line. So I'm a little bit shorter, meaning a little bit slower, and I'm a little more north. All right, this is just kind of classic. There are three forces tugging on this thing. Find the result, meaning find the net force on this object. And so I break every vector down into its components. If all of the angles are with respect to the x-axis, then I can just say that all of these are going to be cosines. That's right, that's right, that's left, which is why I subtracted, right? F3 is left. So plus, plus, minus to get the 42.1 horizontally, and then vertically, up, down, up. F1 is up, F2 is down, F3 is up, which is why it went positive, and then a negative, and then a positive, and I get this 36.1. So the resultant is 42.1 to the right and 36.1 up. I do the Pythagorean theorem to get the actual magnitude, and then I do inverse tangent to find the angle. And as you can see, it is in the first quadrant because the resultant is to the right and up. This is a classic boat question, so we want to cross the river without floating downstream. Remind yourself, the only way you don't float down or float up is if your vertical component is exactly the same size as the current. Because then when you add the vectors, those two components will cancel, and you'll be left only with the dotted line. So what you're really doing is you're going to take your 18 and angle it up the river and go down 4, and then you're left with that guy as your resultant, okay? And the angle is going to end up being inverse sine of 4/18. So it looks like that's like a 12.8. If you don't make any corrections, right, so you're just pointing the boat straight across, well, now you're going to go across horizontally at this. Well, your horizontal is just the boat, 18. You're going to go 180. It's going to take 10 seconds. And then vertically, if you don't make any corrections, the only thing that's affecting you vertically is the current. So you're going to float 4 meters per second downstream for those 10 seconds, and you float 40 meters downstream. Your speed is, of course, the Pythagorean theorem of those things, and you get 18.4. The ship located, naval base. Okay, this one is all just about the three-dimensional Pythagorean theorem. You need to figure out how to find delta x. And again, this is going to be up to you. The plane looks like it is right and down, and the ship is left and up. When you do delta x, you are doing x2 minus x1. It is the difference between those values. But if you take the plane minus the ship, well, it's really a positive x value minus a negative x value, which is really the same thing as just adding those two values together, which is what I did here, right? This is how far the ship is left, and this is how far the plane is to the right. And if you add those together, you get the actual difference between their positions. And again, that plus sign is really a minus of a minus. Same thing for the y's. One is up, one is down. The difference between them, you can just add them together to find this. But again, you're really subtracting a negative. And the height-wise, well, the one is just up and the other one's on the ground. So delta H is just the 3. And we know that the 3D Pythagorean theorem says that the distance in 3 dimensions is just delta x squared plus delta y squared plus delta h squared square rooted. All right. This next one's like a classic equilibrium question. So this is where we're going to set both the x hat and y hat forces equal to 0. Why? Well, it's not accelerating. If it's not accelerating, that means the forces must be balanced. So I just look at horizontally what's going on. Right? In x hat, T2 cosine 30 is how far to the right T2 is pulling. T1 cosine 45 is how much left T1 is pulling. The right minus the left equals 0. And then I do the same thing for the ups, right? The up plus the up, right? Both ropes are pulling up minus the weight equals 0. And all I did here, it looks like I took this equation and I solved it for T2, which is what is circled, and then I plugged that in, meaning substitute that in for T2 in the bottom equation, which gives me this, and then it gave me that, and I just went ahead and solved algebraically. And again, you can graph, you can just end up with one equation, one variable. You can solve it however you want, actually. You could have solved both of these for T1 and graphed it in terms of T2 and found the intersection. I don't actually care, but once you get this set up, you end up with 2 equations and 2 variables. It is no longer physics. It's just algebra. Solve it however you want. Oh, and the last one, looks like I gave you what would happen if you, this is some A and this is some B, and I think I just gave some examples of what this is actually numerically and what it would be. And then the same thing here. This ends up being that negative 2A plus B is equal to C, and I kind of show a picture of how those vectors would add together. And again, when you subtract a vector, you just go opposite of what it is. But these are kind of just fun questions, but the first 6 are absolutely on the test. You absolutely need to take vectors in component and angle and magnitude form and go back and forth. You are going to do a plane and a wind. You're going to do a force question where you have like 3 or 4 forces, and I want the resultant of them. You're going to have a boat crossing a river. You're certainly going to have some sort of ship and helicopter where it's a 3-dimensional Pythagorean theorem. And then you might have 1 or even multiple equilibrium questions where we're setting the forces equal to 0. And when I say forces, force is a vector. And so we have to look at the components of the forces equaling 0 and then solve some sort of system.